Okay, now we're ready to define the set of real numbers. All we need is one more definition. Now I'm going to define a set here, which is the set of irrational numbers. We are not really going to use this set too much in terms of what properties it has, but we will be working with some of its elements. So let me write something here. The set of irrational numbers and I'm not going to give it a name in terms of symbols. However, if you look at the literature, usually this is denoted as set R, set minus Q, the set of rational numbers. So set of rational numbers, R set minus Q, or set of real numbers set minus the set of rational numbers. Now, what are the irrational numbers? Are all of the numbers that have an infinite number of decimals without any patterns. And repetition is included as a pattern. Okay. So what are examples of irrational numbers? And again, like I said, these are ones that we're going to use, but in terms of their properties, we're not going to use too much. Okay. But let me give you an example. So let's do, what example is this? This is example, oh, so this was example 6 here. Forgot to write that down. So example 7. Let's write some elements of the set of rational numbers. So the following are elements of the set of rational numbers, which again, if we have to denote it, we write it as the real numbers set minus the rational numbers. Okay, so what do we have? Square root of 2 is an irrational number. If you plug it into your calculator, for example, you're going to see that, well, you can't show infinitely many decimals in the calculator, but you can see that there's as many decimals as we can find, and there's no sort of pattern. There's no repetition. There's nothing like that. Okay, so this is approximately 1.414213562, etc. And you're never going to see a pattern. Another irrational number is pi. Now, pi, if you remember, comes from a ratio of the diameter and circumference of a circle. For us, it's going to be very important in trigonometry portion of the class because we're going to be studying circles in trigonometry, and pi has this natural relationship to circles. It's the ratio of the diameter and the circumference of a circle. What's pi? Pi is approximately 3.141592654, etc. And again, there's no repeating pattern. Another one, Euler's constant, E. This is used for exponential functions, base E. So what is this approximately? This is 2.718281828, etc. without any pattern. What are examples of numbers that are not irrational? Well, but 1/3, which is, let me use the notes. So let me write equality, because this is equal to 0.333 repeating, right? And since I'm putting the best repeating infinitely, then I can write an equality sign. And that's something that you have to be careful and something that I'm going to point out a lot in the feedback for your reading homework. You only want to use the equal sign if whatever's on the left and right of that symbol are in fact equal. That's why I'm using the approximate symbol here. This means approximately. I use the approximate symbol because I'm rounding, right? I can only give you so many decimal places for each of these 3 numbers. So this is not an exact number. Square root of 2 is not exactly equal to this number that I showed. That's why I use the symbol approximately. But 1/3 is equal to 0.33 repeating infinitely and is not irrational. Why? Because there's a pattern to the decimals, right? It's just repeating. That's a pattern. 3 repeating infinitely is a pattern. So that is the difference between irrational and rational numbers. Every rational number you can always write as a ratio of integers or as a infinite decimal or finite decimal with a pattern. If it's infinite, there's going to be some sort of pattern like here, 1/3 equals 0.33 repeat. For irrational numbers, there's always infinitely many decimals, and you can't ever find a pattern to their decimal, meaning that you can't ever really say, okay, I know that from here, these are going to be the decimals onto forever, right? Because you can't really count all of them. They never repeat. There's no pattern. In terms of computer science, if you've taken any computer science class, or if you are going to take a computer science class, you're going to say that these numbers, the irrational numbers, contain a lot of information. While rational numbers and integers do not contain a lot of information because it's easy to identify their patterns. Now that we've done this, we can finally write what the set of real numbers is. So what is the set of real numbers? And here, let me introduce a symbol. This symbol here that looks like an arrow with 2 horizontal lines, this means implies. I'm going to be using this symbol a lot in the notes, okay? So now we know what the set of rational numbers are. We know what the set of irrational numbers looks like, but we don't know all of the irrational numbers, but we know what some of the elements look like and what defining properties they have. So what's the set of real numbers? Well, this is just the set of rational numbers union the set of irrational numbers. Geometrically, how do you want to think of this? This is just the number line. So think of the number line. We have 0, 1, 2, etc. -1, -2, -3, etc. So what's the set of real numbers? It's this number line here that goes off to infinity on both sides. All of this. And notice that any number here, no matter how small, how close you make those numbers there, all of them are either rational or irrational. So whenever you want to think of the real numbers, think of this number line here, and this is usually called the real number line. Meaning that there are no gaps. If we were to do a number line just for the rational numbers, there would be gaps all over. Same if we did a number line for the irrational numbers, there would be gaps all over. However, if you're using all real numbers, there are no gaps at all. No matter where you put one of these numbers, that's always a real number. Doesn't matter where you put it. Now we're going to be working with real numbers for basically all of the class, mostly with rational, but also irrational numbers. If time allows, I might introduce complex numbers, especially when we're talking about polar coordinates, if we get to that. Complex numbers are very important, a lot of good geometric interpretations, right? But we're going to get to that eventually. For now, this is what we're going to need in terms of sets.